it will continue, and we will have only pleasant memories for our stay. And so today's topic will be very different from the topic of my talk a week ago, and I will be talking more about graph theory, and it will be about graph coloring, which is the area of graph theory that I work a lot in. And I will be presenting results which are joint work with several people. They all have now different affiliations. So one of them is Tomáš Kaiser from the University of West Bohemia in Pilsen. Another one is František Kardoš from the University of Pavel Josef Šafárik in Košice. And Andrew King, who is now a postdoc in Columbia University and just got his PhD from McGill, and Jean-Sébastien Sereny, who is a CNRS researcher in the AFA in Paris. So the talk will consist of 4 parts. At the beginning, I would like to recall what graph coloring is, I assume you're familiar with the concept of vertex coloring. I will briefly recall edge colorings, and I will define total colorings, which is one of the standard concepts, but maybe a little bit less known than vertex and edge colorings. Then I would like to say a few words about fractional graph parameters, and when I would like to state the problem we were interested in and our contribution, and briefly say a few words about the main idea behind the proof without giving too much technical details, but probably my goal would be that you get the feeling what the proof looks like. So the central object of this talk is a graph, which I assume most of you are familiar with. It's a combinatorial object that has vertices and edges. Edges joined pair of vertices, and pairs of vertices joined by an edge are said to be adjacent. In a vertex coloring, we want to assign colors to the vertices. So for instance, blue, red, or green, in such a way that any 2 vertices that are joined by an edge that are adjacent receive distinct colors. So for instance, these 2 vertices cannot be colored both blue. And the minimum number of colors needed to color the vertices of a graph, it's called its chromatic number, and is denoted by chi g. So for instance, the chromatic number of this graph, which is the cycle of length 5, is 3. The chromatic number of this graph is 5. These 2 colors should be different. This is green and this is kind of yellow brown. And the chromatic number of this graph is 3, and the coloring is given in the picture. So it is easy to see that the number of colors in an optimal coloring never exceeds the maximum degree plus 1. So this is a trivial bound, and what you do is you just color the vertices greedily, and when you come to a vertex, it has at most delta neighbors. If you have delta plus 1 colors, you still have a color that you can assign to a vertex. And the famous Brooks theorem from 1941, which is one of the oldest theorems in graph theory, asserts that the bound can be improved by 1 for connected graphs unless the graph is either complete, so this is a kind of this exception, or it's an odd cycle, so which is kind of this exception. So for instance, this graph has maximum, so here the bound can be even further improved. This graph has maximum degree 4, and its chromatic number is only 3. So vertex colorings are probably the most studied concept of colorings in graph theory, and another quite well-studied concept is edge colorings, which is the concept where we want to color the edges. So we're coloring the edges of a graph in such a way that whenever 2 edges share a vertex, they must receive distinct colors. So for instance, in this graph, this edge, and this edge, these 3 edges, they must receive distinct colors. And the minimum number of colors needed to color the edges of the graph in this way is called the chromatic index of a graph. And clearly, if you have a vertex that is incident, in this case with 3 edges, then the number of colors you need is at least 3. So the maximum degree in your graph is a lower bound on the number of colors you need. Because if you have a vertex incident with delta colors, all these delta edges must get distinct colors, and therefore the chromatic index is never smaller than delta. On the other hand, a famous theorem of Wissing's from 1964 asserts that the chromatic index of a simple graph, that means a graph that doesn't have parallel edges or loops, is either delta or delta plus 1. And actually it's very hard to distinguish between the classes of graphs for which the lower bound holds and for which the upper bound holds. In fact, it's NP complete to decide whether a graph has a delta H coloring if it's a delta regular graph for delta at least 3. So one example of a graph with maximum degree 3 where you need 4 colors is this graph. So let us have a closer look at it. So here we have a triangle. So these 3 edges, any 2 of them have a common vertex, wherefore these 3 edges must be colored differently. So without loss of generality, this edge is red, this edge is green, and this edge is blue. So if there was a coloring using 3 colors, then this edge must be red, because this vertex already is incident with a green and a blue edge. This edge must be green, because this vertex is already incident with a blue and a red edge. And this edge must be blue, because this vertex is already incident with a green and a red edge. So now, this edge, look at this edge. This edge cannot be red because of this edge. It cannot be green, and it cannot be blue. Therefore, you needed a 4th color here, and there is no coloring with 3 colors. So this is an example of a graph with maximum degree 3, where 3 colors are not enough to color the edges. And as I already said, the theorem of Wissing asserts that delta plus 1, in this case 4 colors, will always suffice. So the concept of colorings that we will be looking at during this talk is the notion of total colorings, in which we color both the vertices and the edges of a graph. And the constraint is that any 2 adjacent vertices, like these 2, this one and this one, must receive distinct colors. Any 2 incident edges, that means edges sharing a vertex, like this one and this edge, and any edge incident with some vertex, they must also receive distinct colors. So for instance, this green edge and this blue vertex, they must have distinct colors. The minimum colors one needs is called the total chromatic number of a graph, and is denoted chi with index with subscript t. And a famous conjecture of Behzad from 1965 has said something that's a conclusion similar to Wissing's theorem should hold. So if we think of a lower bound, if we have a vertex of degree 3, for instance this one, then we need 3 distinct colors to color the edges incident with it, and the 4th color for that guy. So the total chromatic number is always at least delta plus 1, and Behzad's conjecture asserts that the total chromatic number never exceeds delta plus 2. So for the edge colorings, we know that it's true, it's either delta or delta plus 1. For total colorings, it's conjectured that the total chromatic number is always either delta plus 1 or delta plus 2. And the best result towards the proof of Behzad's conjecture in general terms is the result of Molloy and Reed from 1998, and they managed to prove not with plus 2 but with some plus huge constant. So this is the currently best known general bound. The Behzad's conjecture is known to be true for small values delta, if I am not mistaken, up to delta equals 6, but I am not completely sure of the state of the art in this area. So let us now move to fractional graph parameters, which will be the notion that we will be looking at during this talk. So far we have seen the ordinary colorings. So every vertex was assigned 1 color, and we had some constraint that certain objects like edges or vertices in our graph must receive distinct colors. So in a fraction, so the usual coloring, we can understood it as a partitioning of vertices into disjoint sets, which we called color classes. In a fractional coloring, we don't want the color classes to be necessarily disjoint, and rather we want to assign them some weight that tell us how well this color class covers the elements contained in it. So I will give an example in a second, but let me go through the definition first. So we consider color classes, which in case of vertex coloring there should be independent sets, in case of edge colorings there should be matchings, in case of total colorings there should be total independent set, and these color classes need not to be disjoint, but each of them is assigned a weight. And the constraint is that if we look at any element, any vertex or any edge, and we look at the weights of the color classes that contain this particular element, and we sum these weights, then the sum we get must be at least 1. So every element is covered by the sets of total weight at least 1. And what we want to do is, we want to minimize the total weight of all color classes. So for instance, if the weights can be only 0 or 1, when the independent sets that has weight 0, they do not contribute to either of these two bounds. And those that have weight 1, they already cover their elements. So if we restrict the weights to be only 0 or 1, then this constraint says that every element is in at least one of the color classes, and this constraint says if we want to minimize the total weight, then we want to minimize the number of color classes whose weight is 1, and these are actually the color classes we're using in the coloring. So if we restrict the weights to be only 0 or 1, we're getting an ordinary coloring. And if we don't restrict, then we probably can use the independent sets of less total weight than the chromatic number, and the quantity, this minimum, is called the total fractional chromatic number of a graph. So maybe let me give an example. So let us look at total fractional colorings of the cycle of length 5. And on one of the previous slides, we saw a total fractional coloring using 4 colors. And an easy argument actually says there is no total fractional coloring, the ordinary one, using only 3 colors. So the total fractional chromatic number of the cycle of length 5 is 4. So let us look, the total chromatic number is 4. So let us look at the total fractional coloring. So one possibility would be to consider these 5 total independent sets. So by a total independent set, I mean a set which contains vertices and edges, such that there are no 2 adjacent vertices, no 2 edges sharing a vertex, and no edge incident with one of the vertices in the set. So they're valid as color classes, and assign each of them weight of 1/2. And when consider this set, this is not completely independent set, okay, small mistake. So forget this set. So this would be total independent set. So maybe this wasn't the best example that I started with. I'm sorry for that. And it's the first time I'm talking about this result, so it's not like completely without all mistakes. So, but let me go through this like as far as I can. So we want to assign these total independent sets. This is not quite independent. Weights in such a way that whenever I look at one of the elements, for instance this edge, and I look at the sets that contain that element, so this is this and this set, and I sum the weights, so I sum this 1/2 and this 1/2, I get 1. And similarly, if I look at any vertex like this one, and I sum the 2 weights, I get at least 1. And then if I sum the weights of all the sets, then I am supposed to, what I want to get is what I want to minimize this sum, and this sum is supposed to be the total fractional chromatic number, which I said is equal to 3, but unfortunately the set that I presented to you does not witness it, because by mistake this one is not total independent.
So is it nearly 3?
I would have to think.
What is the total independent? I think I missed.
So the total independent is a set that can be a color class in a total coloring, and in total coloring we want to assign colors to edges and vertices in such a way that no 2 adjacent vertices have the same color, no 2 edges sharing a vertex have the same color, and no edge and no vertex incident with it has the same color. So a set is total independent if it's a set of some vertices and edges. It doesn't contain 2 adjacent vertices. So for instance, this set is not total independent because these 2 vertices are adjacent. All the edges form a matching, and there is a no edge and a vertex containing it. So for instance, if I add this vertex to this set, it won't be total independent anymore because this edge would contain this vertex. And these are sets that can actually appear as color classes. So in an ordinary coloring, I either take it or leave it. in the fractional coloring, I say I'm taking it like maybe half or with 1/4, and I want each element to be covered by sets of total weight at least 1. And I minimize the sum of total weights of all the sets. So I can view it as a kind of a linear programming relaxation of an ordinary coloring. So sorry for messing up this example, but let me go through some basic results on fractional colorings. So now I want to survey the results on fractional vertex colorings and fractional edge colorings, and later, to motivate our work, I would like to say a few words on results on total fractional colorings. So first of all, if I take an ordinary coloring of a graph and then I assign the color classes weight 1, then this is a valid fractional coloring. So the fractional chromatic number is always smaller or equal the ordinary chromatic number. And similarly for the fractional chromatic index and the fractional total chromatic number. And the gap between the two quantities can be arbitrarily big. So for instance, the chromatic number can be arbitrarily big and the fractional chromatic number of a graph can be arbitrarily close to 2. So there are graphs whose fractional chromatic number is at most 2 plus epsilon for any given epsilon, and the chromatic number is 10 million, billion, any number you prescribe. And if we look to cubic graphs, for instance, then one can think that if the graph locally looks like a tree, then its chromatic number or the fractional chromatic number should be small. So it's known that you can have a cubic graph with arbitrary large girth whose chromatic number is 3, but if you look at the fractional chromatic number, then there's an upper bound 2.416 due to Wormald. So it's known that if you have a cubic graph and it has large girth, then the fractional chromatic number is bounded away from 3. On the other hand, it's also known that as the girth grows, when the fractional chromatic number does not approach 2. And there's a construction of graphs which are cubic, have large girth, and where fractional chromatic number is at least 2.196. However, a completely different phenomenon appears for the fractional edge coloring. So first of all, an easy consequence of the structure of the perfect matching polyhedra is that the fractional chromatic index of a cubic bridgeless graph is always equal to 3. So we have seen that the chromatic index of a cubic graph is either 3 or 4. We know there are snarks, which means there are graphs which are cubic and bridgeless, and you can color the edges of those graphs with 3 colors. So in general, the chromatic index of a cubic bridgeless graph can be 4. However, if we restrict our attention to the fractional chromatic index, then we know that the fractional chromatic index is equal always to 3. And by bridgeless I mean there is no edge whose removal would increase the number of components. And if we look to general graphs with general maximum degree delta, then if the graph has large girth, then of course the fractional chromatic index is at least delta, because if I look at the edges incident with the vertex of maximum degree, when each of them is in independent sets in the line graph of total weight at least 1, these sets must be different because no two edges sharing a vertex can be in the same one. So the total weight of all the independent sets in the line graph must be at least delta. So clearly the fractional chromatic index must be at least delta. And on the other hand, for fixed delta and for every positive epsilon there exists a girth such that if I take any graph with maximum degree delta and at least that girth, the fractional chromatic index will be at most delta plus epsilon.
So can you remind the girth what girth is?
Oh, and okay, so maybe so since this will be quite central, let me write it on the board. So the girth is the length of the shortest cycle. So the graph has girth at least 5 if it doesn't contain any cycles of length 3 or 4. It has girth at least 10 if it doesn't contain any cycles of length between 3 and 9. So let me move to the problem that was of interest to us, and so we were interested in fractional total colorings. So as I already mentioned, one of the most open problems in the area of total colorings is the conjecture of Bergshut, that every graph has a total coloring with at most delta plus 2 colors. And this conjecture has been proven in the fractional setting by Kyriakos and Reed, and they prove that if you, instead of the total chromatic number, you consider a total fractional chromatic number, then the total fractional chromatic number is bounded by delta plus 2. And we were also interested for which graphs the equality hold, and we managed to prove that if the equality hold and the graph is connected, then it's either a complete graph on an even number of vertices, or it's a complete bipartite graph where the two parts of the graph have the same sizes. And for all other graphs, the total fractional chromatic number is strictly less than the maximum degree plus 2 for all other connected graphs. So motivated by his result, Reed asked what we can say about graphs with large girth, and he made the following conjecture. So he conjectured that as the girth grows, the total fractional chromatic number of a graph should approach delta plus 1. So to be more precise, he conjectured that for every integer delta and every positive real number epsilon, where exists girth g, such that every graph with maximum degree delta and girth at least g has total fractional chromatic number at most delta plus 1 plus epsilon. So the delta plus 1 is clearly a lower bound. The total fractional chromatic number cannot be below delta plus 1, and the reason is if you take the vertex of maximum degree and you take the delta edges incident with that vertex, when these delta edges and the vertex, neither of these two objects can be in the same total independent set. Each of them must be in total independent sets of total weight at least 1. So you need the total independent sets whose sums of weight is at least delta plus 1. And he conjectured that as the girth grows, then actually you can get as close to the lower bound as possible. So this conjecture is easy to verify for delta equal 1, where you have just matching, so there's nothing to not too much to say about. For delta equal 2, you have paths and cycles. So for paths, the total chromatic number and the total fractional chromatic number is 3, and for cycles you can actually easily see that as the length of the cycle grows, the total fractional chromatic number approaches 3, but there are some cases where it's not equal to 3. And the life becomes more interesting when delta is 3 or more. So we have two results in this direction. The first result is the proof of conjecture. So with František Kardos and Jean-Sébastien Sereny, we were able to prove the conjecture exactly as stated by Reed. So for every delta and every epsilon where exists some girth g such that any graph with maximum degree delta and girth at least g has total fractional chromatic number at most delta plus 1 plus epsilon. And we were able to obtain actually a little bit more surprising result for certain values of delta, and this is a joint work with Tomáš Kaiser and Andrew King. And we were able to show that if delta is 3, or delta is an even integer greater than 2, so 2 is somehow exceptional, when there exists some girth g such that any graph with maximum degree delta and girth at least g has actually total fractional chromatic number equal to delta plus 1. We know it cannot be below delta plus 1, but we've managed to show that actually this plus epsilon is in these cases unnecessary. Unfortunately, we're not able to say whether it's necessary for delta equal 5, 7, 9 and so on. We believe it might not be necessary, but unfortunately the proof we used to obtain this result doesn't translate to cases where the maximum degree is 5, 7, 9, and so on.
So why is this 3 special there?
You will see from the proof. So I would like to sketch the main idea behind these results without going to too many technical details, but still I hope that there will be enough that you will get enough feeling how the proof goes. So the proof is probabilistic, and it's based on the following observation, that proving that the total fractional chromatic number is at most some alpha was the same as describing a probability distribution on total independent sets such that each element is included to a chosen set with probability at least 1 over alpha. So again, if I want to prove that the total fractional chromatic number is at most, let's say, 5, if I give you a probability distribution on total independent sets such that if I fix any element in my graph, any vertex or any edge, when the probability it's included in a chosen set is at least 1 over 5, then I know that the total fractional chromatic number is at most 5. And this is actually very easy to observe. So if A is total independent set, and I'm going to choose it with probability PA, then if I assign weight to this set, which is equal to PA times alpha, then I claim I get a total fractional coloring. And the reason is that since before every element was in a chosen set with probability at least 1 over alpha, when the weight of the set containing it is at least the sum of the probabilities times alpha, which is 1, and the total sum of all the weights, where before it was 1 because it was just the sum of the probabilities, and after multiplying by alpha the total weight is equal to alpha. So instead of constructing the coloring, we will be rather interested in constructing a suitable distribution on the total independent sets. And in the next couple of slides, I want to restrict to one particular case, namely the case of cubic bridgeless graphs. So for this slide and the next 2 slides, for simplicity, I will assume that the graph we want to find a total fractional coloring of is cubic and is bridgeless. Cubic means that all the vertices have degree 3, and bridgeless means that it doesn't contain an edge whose removal increases the number of components. So the first observation is that where exists a distribution on perfect matchings in the graph such that every edge is included in exactly 1/3 of these perfect matchings. So where exists a probability distribution on perfect matchings such that if I fix an edge and I choose a matching, when the probability that edge is included in the chosen matching is equal to 1/3. And this is an easy consequence of the description of the perfect matching polytope, since it's well known that the perfect matching polytope of a cubic bridgeless graph always contains the vector whose all entries are equal to 1/3. So now we randomly choose a perfect matching and we look at the complementary 2 factor. So the complementary 2 factor is comprised of cycles, and because of the girth assumption, these cycles have girth at least g. There are no cycles of length less than g, so these cycles have length at least, each of them has length at least g. So what we now do is that we remove some vertices from these cycles, and roughly we remove vertices at distance g over 100, and this 100 is here rather a randomly chosen constant which slightly varies in the proof, but let's say it's g over 100 now, and we obtain a collection of paths whose length is at most g over 100. And what we do is that if we have this long cycle, we have g over 100 possibilities how to remove these vertices. You can remove one set of vertices, or the set rotated by 1, rotated by 2, and so on. So we randomly choose which of these possibilities we're going to use. So now I have a random collection of paths, and let us look what's the probability that an edge is included in that collection and a vertex is included in that collection. So an edge is included, so first of all, it shouldn't be in the perfect matching. So it's 1 minus 1/3, it's 2/3. And then it shouldn't be an edge incident with one of the vertices I removed. So an edge is included in this collection with a probability slightly less than 2/3. And a vertex is included or is covered by one of these paths with probability almost 1. It just shouldn't be one of these vertices, but the portion of these vertices substantially decreases as the girth grows. So the vertex is included with probability 1 minus 100 over g. So now I have this collection of paths, and I want to construct a good distribution on total independent sets. So what I am going to do is the following. So I have this collection of... Yeah.
In the previous one, each vertex is, so is it, so the set you get is not yet independent set?
No.
Just path.
These are just paths. So what now I am getting is just a collection of paths whose length is g is at most g over 100, and I'm not saying, and when I want to do something with this path, I remove some vertices of the graph. These vertices that I remove are gone. They will not be included in the total independent set that I am constructing, but the remaining vertices, they will have some probability to be included. Other questions? So if there are none, so let us look at the actual construction of the total independent set. So I have the paths, and for each of the paths I will randomly choose a level to which I am going to assign that path. So let's say I will be assigning paths to 10 different levels. So for every path in the collection that I obtain, I will throw a coin and assign it a number between 1 and 10. And now what I am going to do is, first I will define what elements I will include to the total independent set for the paths in the first level, then in the second level, then in the third level, then in the fourth level, then in the fifth level, and so on. And the way I will do it, it will be just a greedy way. So maybe let us look at one particular example. So let's say I have this path, and this path was assigned to be on the third level. So it's a path on the third level. So these edges that goes from the path, these are edges contained in a perfect matching, in the random perfect matching that we have chosen at the very beginning. And the mates of these guys, they contain also in paths. Well, there's some negligible probability that a mate of that guy can be one of the vertices we removed, but let's pretend it's not the case. And some of these paths are already on the levels, on the previous levels. So that means they're included either in the first or in the second level. And some of these paths, like for instance this one or this one, are on higher levels. So maybe the fourth or the fifth. And some of these paths, maybe like this one, were on the same level as this path. So the paths that appear on the previous levels, we already decided which edges and which vertices we're going to include to our total independent set. So for instance, we included this edge, this vertex, this edge, this edge, this edge, and this vertex. So now I want to decide which of these vertices and edges of this path, and now I'm going from left to right, I'm going to include to my total independent set. So assume this edge is already in the set. So that means I cannot put in my set this vertex, because this vertex would be adjacent with an edge in the set and it wouldn't be a total independent set. I cannot include this edge either, because there would be two edges sharing a vertex. And I cannot also include this vertex, because it would be adjacent to this vertex, which is not on this path, but very adjacent in the graph to this edge. So it wouldn't be a total independent set. So the first element I can include on this path is this edge. So I do so. So the edge just changed the color from black to blue. I'm not completely sure how visible is it, but this edge is now included in the total independent set. So similarly, I cannot include this vertex and this edge, but when I come to this vertex, I can include it. Its mate is not in the total independent set. So I include it to the total independent set. Now, this edge cannot be included, this vertex cannot be included, but this edge can be included because neither of its two ends is in the total independent set, and I haven't included this edge. So I include it. I just have done so. So it's now blue. And now I come to this vertex. So one would think that, okay, now it depends on the order of the paths on the third level. But in order to minimize the number of dependencies between different events, if my mate is on the same level as I am, I will always consider as being in the total independent set. So I am not going to include this vertex to a total independent set because I don't want to have some dependencies between the paths on the same level. In this way, I will kind of bound the way in which dependency between different events in my graph propagate. So I'm not going to include this vertex to my total independent set, and instead of that I will include this edge. So now I cannot include this vertex, I cannot include this edge either, and I come to this vertex now. So its mate is on a higher level, and if my mate is on a higher level, then I consider it as not being in the total independent set and I include it. So the rule is I include a vertex or an edge as long as I can, with the only exception being if my neighbor is on the same level, then I am not going to include a vertex. And this is just to minimize the propagation of dependency of events on the same level. So the probability that this vertex is included, it will just depend on the result of what happens on this path and the path on the first level. So it's kind of like a tree, and the number of these events that it depends is probably g squared or so. So it doesn't depend, it doesn't grow to two sides on the same level. So there is one more trick that I would like to mention now. So as I said it, I was included everything greedily in my total independent set, but that's not actually the case that what I am going to do. When I come to a vertex, I will not include it with probability 1, but I will include it with a slightly smaller probability. So there will be some psi, some positive psi, such that I throw a coin when I come to a vertex. So for instance, I come to this vertex and I throw a coin, and with some positive probability psi, even if I can include it, I am not going to include this vertex. And the role of psi will be clear from the next slide. So this is the main construction of the total independent set. So maybe are there any questions?
So when you split paths into levels, is it arbitrary or?
Yeah, it's just every path has a probability being at a certain level 1 over 10 in this case, and these probabilities are mutually independent.
And
So 10 actually for our exposition is fixed, but in the actual proof it grows with girth, and the reason is that I want to minimize the probability of this event happening, because this is something pathological and I don't want this to be happening with high probability in my analysis. So in the actual proof 10 grows with the girth. So are there other questions? So if there are no more questions, so let me wrap up. Oops. Okay, we have some technical problem.
Is it the last slide?
No, it's not the last slide.
Oh. My computer stopped working. Oh.
Good.
Right.
Thank you. So thank you. So let us wrap out for the cubic case. So as I already said, the levels are here to guarantee mutual independence of the neighbors of the vertices of a path. So why it was important is that when I look at these guys, I want the event that this guy is in the total independent set and this guy is in the total independent set to be mutually independent as probability events. For that I am splitting it into paths, and because of the girth assumption, were mutually independent. When the role of psi is actually to decrease this probability to 1/4. If there would be no psi, the probability of a vertex to be included in a total independent set would be bigger than 1/4. So once I have a choice of the paths fixed, when a probability of every vertex on a path to be included in the total independent set is exactly 1/4, and the probability of every edge in a path to be included in a total independent set is exactly 3/8. So, this choice just decreases this probability to 1/4. If there would be no psi, this probability would be bigger than 1/4, and I would have to do something else. So the role of psi is just to make this nice. And now, so this was under the assumption that the choice of the path is fixed, and the choice of the path depends on the choice of the perfect matching and the choice of the vertices that I am going to remove from a perfect matching, from the complementary two-factor. So if I consider distribution over perfect matching and the distribution over the vertices that I am going to remove from the cycles, then what I am going to get is that every vertex is included with this probability, because the probability that a vertex is covered by the path was 1 minus 100/g. So I just multiply that number by 1/4. And the probability that edge is included is this number. And as we said at the beginning, if I manage to find you a probability distribution where every vertex or an edge is included in a total independent set with some probability, then I have an upper bound of 1/, that probability. So in this case I have an upper bound of 4 plus something. And that something grows to 0 as the girth grows to 0. So I promised you that in the cubic case I should actually show you the bound without this plus epsilon. I will not do so, but I will just say what you have to do differently. So if you want to show that the total fractional chromatic number is equal to 4, then actually you need here to have exactly 1/4. So what you do is, so you're losing at several places, but one of the places where you're losing the most are the ends of the path, because you remove a vertex and you didn't put that vertex and neither of the three edges incident with that vertex to your total independent set. So what you do is that first of all you make sure that these vertices that you're going to remove were kind of far apart from each other. That it doesn't happen that if you have two cycles, when you remove both this vertex and its mate. So you never remove two vertices joined by a perfect matching. And this can be achieved using some standard argument on distant representatives in graphs. And then what you do is that you kind of resolve possible conflicts or resolve interaction with the total independent set in some uniform way that actually allows you that everything nicely wraps to be equal to 1/4. This is something that requires some kind of finer argument, but rather it's that you have to go through cases and you have to say that the probability of several events happening is the same. So it's not like deep, it's rather technical going through several cases, and there's not too much to think in deep about this particular case. So maybe instead of giving more details on these technical pieces of the proof, let me say a few words why the even maximum degrees and odd maximum degrees differ. So the difference lies in the fact that if you have an even maximum degree, then you can find a uniform covering of the edges by two factors. in the sense that you can find a multiset of the two factors such that every edge is included in the same number of these two factors. So if you have a delta regular graph and delta is even, then you can uniformly cover the edges by a collection of two factors. And this is also true for delta equal 3, because you just consider the complements of the perfect matchings that we started with.
You assume some connectivity.
I assume some connectivity, but for this result I don't need the connectivity, because if I have for delta equal 3 I assume some connectivity, but for bigger delta, for bigger even delta, I don't need to assume connectivity. And then I can just use the result that if I have a if I have a graph with maximum degree delta, I can embed it into a larger delta regular graph if delta is even. And I use the covering of that larger graph. So I don't need to assume any connectivity here. If the graph is not regular, then I will not have two factors, but I will have collections of cycles and paths, but that's fine for my proof too. Unfortunately, the same is not true if delta is odd, and I can find this uniform covering only under the assumption of some connectivity. And the connectivity that I am assuming is that the graph is cyclically delta minus 1 edge connected, and the cyclic connectivity of a graph, the cyclic edge connectivity of a graph, is the minimum number of edges that I have to remove from my graph that I create at least two acyclic components. So in other words, a graph is cyclically 4 edge connected if there is no collection of 3 edges separating two different cycles in my graph. So if delta is odd and the graph is somewhat connected, for instance like this, I can find this uniform covering by two factors too. And then I can prove the result that the bound is actually equal to delta. And actually I can prove something stronger. I can prove, but this time I have to allow some slack. With the epsilon I can prove a stronger result on extending precolorings. So if delta is odd, the graph is connected, girth is high, I can precolor some edges in the graph that are not too close, and I can extend any coloring of those edges to the rest of the graph, any fractional total coloring. So in general case, so this is the induction part of the proof. If the graph is not cyclically delta edge connected, then what I am going to do is I am going to take a cyclic edge cut such that one of the sides is as small as possible and split the graph into two pieces. The minimal piece, by the choice of the cut, if I add something suitable on the other side, will be cyclically delta minus 1 edge connected. Therefore this precoloring result can apply to it. And what I do is I apply induction on the bigger piece. So I decrease the size of my graph since I split it into two. I apply the induction on the bigger piece, and since the smaller piece is cyclically delta 1 minus edge connected, I just use the extending result and extend the precoloring, extend the coloring from the bigger piece to the smaller piece. So, and since I probably don't want to go into more details, I could, but I thought like probably the main idea is with the probability distribution, and I showed you the construction, and I was also told that I should end on time today, so I wanted to be sure I end on time. So I just thank you for your attention.
We still have time for questions.